right, in the last video we looked at how to find a relative minimum, relative maximum using our calculator. But what use is that? Well, we want to look this time at maximizing a real life quantity. So I've already written the problem here. This is the problem that we're going to use. The design of a digital box camera maximizes the volume while keeping the sum of the dimensions at 6 inches. Let's assume this to be a rectangular box. If the length must be 1.5 times the height, what should each dimension be? Remember, we've got several pieces of information that we know. We know that the length is 1.5 times the height. We know that the sum of the dimensions is equal to 6. So let's define our variables and set ourselves up a polynomial. We're going to say here, we're going to use x to mean the height of our box here. And since we know that the length has to be 1.5 times the height, we will define our length as being 1.5x. Well, that part's pretty straightforward. Here's the part that we need to think about. We need the width. Length, width, height. So we still need the length. So how are we going to find that? Well, we were given another piece of information. The sum of the dimensions is 6. So length plus width plus height has to be 6. So how do I find the width part? Well, it's just a leftover part. 6 minus the height of x minus the length of 1.5x gives me 6 minus 2.5x. So we're going to use that as the width of our box. From that, I can find an equation for volume, because that's what we want to maximize. Maximize the volume. So I need to write an equation for volume since it's what I want to maximize. Well, how do you figure volume of a rectangular box? It's length times width times height. So the length here was 1.5x, the height was x, and the width was 6 minus 2.5x. So I'm going to write this like this. X times 1.5x times 6 minus 2.5x. And you can actually, in this problem, leave it in that form. You don't necessarily have to change this to standard form, but I'm going to do the distribution and change it to standard form. And in standard form, that gives me the equation 3.75 x cubed plus 9x squared. If I just multiply all of that out, that is the equation of the polynomial for height. So I want to maximize it. So what am I going to do with it? Well, the easiest way to find a relative minimum and maximum here is to graph this on your calculator. So let's get us some room on our screen here. Let me clear this off. And let's graph on the calculator. You would do well to do this along with me. This function. And my function was f of x is equal to negative 3.75 x cubed plus 9x squared. Now, you may have to play with your window in order to get this to graph. So if you need to play with your window, play with your window. You need to get it until you can actually see the shape of the graph. Well, if I play with this long enough, I can get a graph that looks sort of like this. There's my cubic function, and I know, okay, I'm going opposite directions since that's odd and that's negative, so I'm going down to the right, I'm going up to the left. So if I find the place where I have the maximum volume, what am I looking for? Well, I'm looking for this point right here. Can I use a point over here? Obviously, that function would have a higher value here than it would here, but why can't I do that? Well, because I'm in negative x territory over here. I can't very well have a negative x value. X was my height. I can't have a height that's a negative number. So I'm looking for the value right here. So if I'm looking for the value right there, let's do that on our calculator. We do second calc maximum, and it gives me x equals 1.6, y equals 7.68. All right, well, what does that tell me? Well, my x value in my function was my height. X is height. So if x is height, the place where I have a maximum volume, the height of this function, of this box, is 1.6 inches. Well, we also said that our length was 1.5 times our height. So if it's 1.5 times our height, it's 1.5 times 1.6. The length of this box is 2.4 inches. And then what about the width? Well, the width of this box was 6 minus 2.5x. So 6 minus 2.5 times 1.6, which is 2 inches. So the dimensions of the box with maximum possible volume would be 1.6 inches by 2.4 inches by 2 inches. But what's the maximum possible volume? You know, what if I'm not really interested in what are the dimensions of the box, but what volume can I actually get out of this box? And sometimes I'm interested in both. Well, so my maximum possible volume is the y value. Remember, I was graphing volume. So what's the biggest volume can ever be? It's this y value here at the top of this. So it is 7.68. We're talking about volume, so cubic inches. One more little point that I want to make here is, let's talk about what the domain of this function is. If I'm looking at what are the valid values of x, can I have x equals -1, x equals -2 in this problem? No, I can't have a height, which was my x value, that's negative. So this is irrelevant. Can I have a volume that's negative? No, so this is irrelevant. So if I determine the value of this x-intercept and this x-intercept, I have the domain of the function. And what I find is the domain of this particular function is the values from 0 to 2.4. That my values for x can only be between 0 and 2.4 if I want to get a legitimate answer. Otherwise, I either have a height that's negative or I have a volume that's negative. And remember, it cannot be exactly those values, because if it was exactly 2.4, I would have a volume of 0. If it was exactly 0, I would have a volume of 0. And I want it to be exactly, which means these are parentheses and not brackets when I state the domain of my function.